Swayam Prabha. Digital India. Educated India.
First question, yeah, you have to go to the back of your booklet. I've got these two so this is NSGA2. So I want you to do one simulation of NSGA2, so you have an idea of how a EMO algorithm works. So you have 5 points coming from parent PT and 5 points coming from QT. Like the example I showed you, there you had 6 points, but here you have 5. These are the I'm not giving you x1, x2. These are f1, f2 value directly for a problem. Okay. So I have to we have to look at this. I have to minimize first objective and maximize second objective. I made it a little complex. So what are you going to do? You first of all you have to convert them into minimization. So how do you do? Multiply f2s by -1. All the f2 values by -1. Also here -1. The first thing to do. Otherwise you will have error. Okay. F1 don't touch anything. F1 is already to be minimized. All right. So once you've done that, you can plot them on a f1, f2 plot. Each of these points you can put it on a f1, f2. There will be 10 points in total. So it will be like that. Here I cannot plot for some reason. So so this is your f1, and you have, I'm just putting here minus f2 because you multiplied by minus, and you have all these points will be there. Some of them are 1, 2, 3, 4, 5. Others are A, B, maybe C, D, E, something like this, right? Now, looking at this plot, you identify the first class of points. Can you do that? You have to see which points do not have anything on the third quadrant. So this one, in this case, this one, maybe if it's slightly below that one. Okay? And then identify the second class. Then you temporarily discount, and maybe these two comes in, and then third class, and so on and so forth. So then in NSGA3, NSGA2, all of this is going to the population PT plus 1, and then second one, if there are 2 left, you just choose these 2. If there are more than 2 left, then you have to do the crowding distance. Before that, this set, let me put some more points in this set, 2 and maybe 3 here. Okay, so there are, let's say, 4 points I choose, and you isolate these 4 points, and let's say you have to choose 3. First thing you do is normalize. Make this 0, f1, f2. Make this 0, make this 1, make this 0, make this 1. Yeah, somebody asked me how to do this. So if you do f min, so find out the minimum value for f1, maximum value for f2, minimum value for f2, f1, let's say, I will do this way properly, 1 min, 1 max, 2 min, 2 max. Then any f, if this one has f1 comma f2, this can be mapped as f1 dash comma or hat comma f2 hat, and each one of them fi hat will be fi minus fi min over fi max minus fi min. This is the way you normalize. Okay, you know these values. So if you put this solution, f1 min is fi, so you put f1 min here, you get 0, so this will become 0. If you put f1 max here, then it cuts out this one and you have 1, so it will be 1. Same thing will be over there. So first thing you do is so you've got f1, you've got points 1, 2, 3, 4, 5, and then A, B, C, D, E. So you have f1, f2 for each of them. First thing you do is do f1 hat, f2 hat, okay, with this normalization. You could do it on Excel. So now you have this, and now make the plot with f1 hat and f2 hat. So I would say make this plot with f1 hat and f2 hat. Of course, you need to multiply it by -1, right? And then you identify these, and then crowding distance you can see already in this one. Apply those things and find the highest crowding distance ones that you have to choose. So tell me what is the PT plus 1, which member from 1 to 5 and which member from A to E be there in PT plus 1, and there should be exactly 5 members because the population size is 5, right? So 5 of them will be deleted, 5 of them will move forward. Which are those 5s? That's the first part. Make sense? No, no other thing. Just this is the tournament selection, but I am not. Tournament selection will be used to create the children, but I have already given you the children. So tournament selection is already implied when I gave you the queue. Okay. So I have reduced the problem for you. You don't have to use tournaments. You don't have to use crossover mutation. All these I have done on PT, and I have given you the QT. So you have PT, QT. You combine together non-dominated sorting, and then which one to be chosen for the crowding distance. Try that. You will have a very good idea of how NSGA2 works. Okay. Okay, next question. This is a hand created problem. So it's a constrained problem with multi objectives. This is again F1, axis, F2 axis. The region inside this weird region, this is feasible. Okay, here is not feasible, and outside is not feasible, inside also not feasible. So this annular part is feasible, and I have got these 10 points here. You have to minimize F1, minimize F2. Can you sort them into different classes of constraint domination? We talked about that, right? So you see, for a infeasible point like for 7, you consider the distance to the nearest constraint boundary as the constraint violation. So 7 has a very small violation because it's very close to the constraint boundary compared to 1. 1 is little away from the constraint boundary, so 7 has a smaller constraint violation than 1. 4 has even more constraint violation than 1. But 10, what is the constraint violation for 10? 0, because it's a feasible solution. Same thing with 8, 5, 6, 3, 9, 2. These are all feasible, there is no constraint violation. Only 1, 7 and 4 violates constraints, and their amounts I didn't tell you, but you can look into the figure and figure out, oh, this one is very small constraint violation, it's almost on the constraint. If 7 was on the line here, it would have 0 constraint violation, and it would have been feasible. So slightly violating, this one moderately violating, this one largely violating. Okay, so now you can apply the constraint domination principle and rank them. All the points that are in the same rank, put them in brackets. So if for example I said here 1, 5 and A, so if I rank them, this one, let's say other points are not there, 2. So this is A 1, 5, so it will be 1, A 5, this is my first rank class, comma, we have 3, comma 4, comma C, comma 2. So this is how I do the ranking. The first one first, this is class 1, then class 2, with the comma, so on and so forth, and all the points in the same class, put it in a bracket. So like that you can write it here. And the last line says, can you also rank the points for single objective minimization of F1? So now if you are interested in only F1, so I am minimizing F1, can you rank them again? So I don't care about F2. Okay, so there will be different ranking. So can you do that? So there will be 2 rankings you are going to put here, one for the 2 objective, one for single objective. This exercise will give you a good idea of how to handle constraints. Okay. These are small exercise here. Okay, this one we just talked about how to compute hypervolume. So here are few points, again minimizing F1, F2. Here is the reference point I gave you. Can you compute how many boxes should be in the hypervolume? So you see these boxes are marked. Can you count? First draw the hypervolume line, the attainment surface line, and count what's the area inside in terms of the number of squares. Make sense? Will this point participate? This is a dominated point by that, right? Will this point affect the hypervolume? Hypervolume is only with the non-dominated points. So this point and that point, whether it's there or not there, it's not going to affect the hypervolume. Okay, it's just a hint. Okay, the final one, It's a little boring, but still you get some idea with the performance metric. Here are my reference set, the P star, the crosses, and here is the performance of an algorithm 1, 2, 3, 4, 5. Note that 3 is getting dominated by 4, okay? Rest all are non-dominated. Can you identify GD? What will be the GD value and what will be the IGD value? GD value again will be distance from average distance from each one of your points to the crosses, closest one. Compute for 1, what's the closest one, and 1 unit this way, 2 units that way, so this is going to be square root of 5 units, 1 plus 4 square root. This one may be closest that one, so it's square root of 2. This one closest that one, so it is 1. Okay, so all that you compute. Would you take 3? No, first thing you have to do for any performance computation is remove all the dominated solutions. So 3 gets dominated by 4, so you're going to remove it, you're never going to use it in performance comparison. Not also here, I mentioned to you already, these 2 will go away, which are dominated. Okay, and IGD is the opposite. IGD, you go for each one of the crosses, you go and see which of the circle is close. So for this one it will be 1, for the second one either 1 or 2 is the same distance, you can take any one of them. For this it's clearly that, for this it's 4, for this it's 5, like that you can do and sum all of them, divide by the number of crosses, that's give you the IGD. So it's the average distance from the reference point to your set. That's it, I think. Okay, so in this one there is no computer needed except for this one you need Excel and a plotting one. Excel has a plotting thing, you could just do a chart, scatter plot, and then you can make that kind of a plot, and this plot is for you to see which is non-dominated, or you can also do this with a little algorithm, or looking at the data you can also say which is in the first front, second front, but plotting always helps. Any question? So these are little exercise for you to understand some details about the EMO procedures. Yeah, usually I give this kind of thing as home assignments for my semester long class, more such problems, a bit more involved. So student really go into it, try to understand each of these, and oftentimes what happens when they're doing, they have new ideas. Instead of doing this, sir, can I do it the other way? And I say, wow, that's a good idea. Let's implement, and oftentimes lead to a paper, you know. So unless you go into the details, you are not understanding it to that level, right? If you only understand that level, oh, my picture comes up, then only you can contribute to the field. Otherwise, you have an overall idea, you appreciate the overall idea, but you will be difficult to contribute. So details are as important as overall idea. Now it's a crash course, so I'm not expecting you to do lot of details, so I'm not giving you a lot of details, but you have some idea about performance measures, you have some idea about visualization. I have not given an assignment here, but also domination check and how NSGA2 works and things like that. Okay, with that I will now demonstrate you. Okay, so there are 100 generation, it's printing every generation the best result, but let me go all the way up. Yeah, so initial generation, so you see it, yeah, initial generation, this was the best out of 20, this is the best fitness I got. Average fitness is quite high, that means their random population, average is really bad, the best is good, and then the best individual has this one, x1, x2, its corresponding function values here. Next generation, it hasn't improved, it could not find anything better than this best. Third, also not. Fourth, yes, it has found now something better, 63 compared to 75, it's minimizing. Then it goes to 60, 60, now almost stuck. In fact, this is very, very close to the optima. I think the optima, as I know, is 60 point something. It's on the simulation I showed you, there was one that goes like this and one that goes like this, and we run and the solution kind of goes and come over here. Remember, that is the one here. So this problem 0.87735 and 60 points. So you see, so it was found way back, it was found only after third generation, and then after that, remember this 63.805, Now it has increased to 60.6707 already in generation 4. This is slightly better, generation 13, even little 12. So at the end, where are we? After 100 generation, we are 60.4321. So minor improvement over many generations. So very quickly comes down, and then so it's like other algorithms as well. So that's the unconstrained problem with 60. Oh no, this is problem 2, I think. I wanted to do problem 1 first. So let me do problem 1 first. Set param problem 1 first. Okay, so I'm going to save it, Control S. And now I'm going to go RGA and first run that. Fortunately it's running. And you got 3,2. I told you it was 3,2, right? You see the function value -8. It's supposed to be 0, very, very small. But where it started, I don't need to go to 100 generation for these small problems. So it started with 8.7. This is the x best value, and then pretty quickly goes to 0.04 function value, 0.4, 0.06, 0.01, 0.009, and pretty quickly gets to -5, then this. Okay, so this works for 2 variable. I could use even small population size. So if I go to, let's say here, and I reduce this to 5 times k, so I have population size of 10. Let's try that. Control S, and now I'm going to run again. Maybe I do less number of generations. So also come here, set param, and going to make it 50. So I do not have to look at so many things. So then run. So 10 generations, 50 generations with 10 population size. Sorry, I have to run the RGA. Okay, now it's not 3,2 crisply, but you see very close to 3 and 2, and function value is this. So that's the effect of population size. If you have little small population size, you get an approximate result. Okay, then you can experiment with it to see where you get start to get satisfactory results. So that's kind of the hyperparameter tuning that you may have to do. So now let's move to constrained version, and I showed you already the constrained version, but let me check with the small sizes what happens. Okay, so now you see it moves to almost the same. We had 60.4 with 20 population size running for 100 generations, but with about quarter less of function evaluations, we get pretty close actually. So this is how it works. Now let's go to true function. So we did the penalty function, right, with case 2. I put a very large penalty because at that case we can get very close to the optimum. Now I'm going to use this penalty parameterless approach that you did the homework. Same problem, same definition, only thing is I'm not adding the penalty here. I'm actually saying let's keep these 2 constraints, and I have a little piece of code that does the penalty parameterless thing. So you see it actually computes the constraint violation and sends the constraint violation value and the function value as 2 different entities. We don't add them with the penalty, we send both, and we have a tournament selection that checks if it's feasible, then it compares the f. If it's infeasible, both, then it compares with the constraint violation. So this is the constraint. So that algorithm is built in here. So we're going to use now case 3. So which means I go to set param 3 and put it to 3. Control S, and we are using the same k equal to 5, n equal to 5 times k, and generation 50. Run. I'm always running the set param. Run here. Okay, it's little better, right? 4.8 with the same we had 60.6. So this penalty parameterless is still better compared to setting up a big penalty and everything. Okay, so now with this code you can put your objective function here, put a case 4 after this, like I said, add your case number here and follow the same thing, copy paste and put your objective function constraint normalized. All constraints have to be less than equal to 0 format, okay, and then go to set param and set your parameters. First thing you do, define your problem, which problem. If you put case equal to 4, then you put 4 here, and then come under here and add one more case where you set up how many variables, constraints, bounds. And then these are your GA parameters, population size and all that, and then you run the RGA code. Okay, now we are going to move to NSGA2. Again, I need your help, come. So I am going to load, so maybe RGA, we have NSGA. First let me delete all of these from here. Okay, it kind of generates some output. You can see them like generation wise, x1, x2, constraint violation, and I think F, all this it puts, then it reports, sorry, this is a report.m, it creates just one output here. Okay. Now going to NSGA2, first I am going to load NSGA2.m. Okay, so here is the code, but don't have to change anything here. Now here we don't have a set param or maybe something like that, but we put the problem description again here. So we will see where the function is. Now the function here is, so here is the selection operator, we have mutation, we have initialization, we have a crossover somewhere, crossover, domination check, evaluation, all of these are non-domination checking and everything is here. It's also plots few things, merging the two population and all that. So now I have to go to problem, problem input I think. Okay. So here it's a little different way we put, again case numbers are there, these are some default problems, problem population size, number of generations, objectives, number of constraints, number of real values. Here you could do both real and binary, like the genius I was showing you about, real, binary, boolean, everything you could do with this. So how many real variables are there? So if you say 1, you have to say minimum and maximum of that. How many binary variables are there? So then you have to show the number of bits that you need, remember. So here is 0, so these are some arbitrary values that I put. But if it's a real parameter 1, then you do lower bound, upper bound, crossover probability, mutation probability, and then eta c, eta m like before. Note that eta c here for multi-objective we put it high, like 10 or 20 or something like that. Okay. Then another case and all that. I think that's it here, everything is put into that one. So let me go and see now what is in, this is problem inputs.m, but where are the problems? Problems are defined in another one, evaluate. Is it evaluate? Wait a second, it must be that one. Yeah. So here it starts, switch the initial part don't touch, then problem. Now here the variables called x real, I comma 1, I is the population number, 1 is the first variable. So ith individual's first variable. I could have done it a little nicer, but that's how it is. So this is f1, this is f2, objective 1, objective 2. It's a very simple problem. Let me show you with maybe Schuffel's function. It's also single, there are number of objectives, how many by 1. I am going to show with 2 variable at least. Fonseca, okay, it's a little complicated function, we could try any one of them. This is also constraint, so let me see, these are 3 objectives, I want to have one with constraint. Case 1 no, Schuffel function has no constraint, Fonseca has no constraint, Kurzave also have no constraint, these have no constraint, ZDT1, ZDT2, 3, 4, no constraint. Okay, let's try with one constraint, let's do ZDT1. Okay, so ZDT1 is number 7, right? There are 2 objectives, first one is here, second one I think I define it here, there is no constraint. Okay, so case 7 we are going to do. So now we go to problem inputs and we'll NSGA2 problem input 7, you see I show you what we have here, 7 and a number of real, so these are commented. So population size 60, so I want about 60 points, let's do 40 maybe is enough. 40 points I want, I run up to maybe 100 generation. Number of objectives 2, no constraint, 30 variables, let's reduce it to maybe 20 or maybe 10. and then minimum variables, and so this should be all 10. So zeros means the lower bound for every variable is 0, ones means upper variable is 1. MATLAB has these two things there as a macro. Real crossover 0.9, mutation 1 over 10 will be 1 over 10 will be this 0.1, usually 1 over n we keep, and 15 I kept for eta c, eta m 20, so that's fine. So this is all defined, right? And now I can go to NSGA2 and choose the problem size number 7. Okay, now it's running. Because there are many points, so it's not displaying each of these points, it's storing in a file. But here we have hooked it up with GNU plot, so it's going to show you a plot, I think. Oh, GNU plot is not here. That's why it's not showing. It's showing something. No, it's actually plotting with MATLAB. You see the Pareto front now, F1, F2, and we got 40 points. Now there is of course this gap here, a gap here, and this will happen in NSGA2. If you keep running, some of these gaps are going to get reduced, okay, because with time it finds that here there is a big crowding distance and these will be emphasized, more points will come here and so on and so forth. Okay. Now I move to maybe a constraint problem. Evaluate. Yeah, ZDT1 it goes from 1 to 1, so I think it's the correct one. I can show you ZDT3 also, but this is with, you see, small population size, it does work. Let's see ZDT3 again. Do I have hard coding? Okay, so I'll leave whatever is 30 variable, but in number 9 I go, NSGA2 number 9, but the issue is that I have set up with small population. No, I didn't change the problem inputs. So now for 9 I'm going to leave all the parameters 100 because I have 30 variables, so I need 100 population size. So that's all fine now. Now I'm going to run ZDT3, which will see a little different from this kind of front. Now 100, it slowed down a bit, you see. There are 100 population members is processing every generation. So it's a little slow compared to the previous one when I had 50 or so. But I think it's a slow computer. It doesn't usually take that long on my laptop. 100 will take a bit of time. Shall we wait or? Okay, let me delete, Control C. Okay, I'm going to reduce the set param, yeah, this one 9. I'm going to do less here, but 30 variables, so maybe I do 60, and maybe this one I do 60 also. Let's see, we'll get somewhere with that. Pop size, number of generation. NSGA2, run. Still little slow. It will speed up because now you have just one front by this time. So the checking of the non-dominated set and all are very easy, very fast now. Okay, now the picture should come up here. Yeah, you see the front? It's disjointed. But I just changed the problem. I didn't change the algorithm, right? So actually there is no Pareto front, no Pareto point here in this gap. It's not that the algorithm could not find, there is nothing there. Because the boundary here comes and goes up like a sinusoid, it goes up, and so those parts are not part of the Pareto front, and the algorithm knows that because it does the domination check, and there are 5 disjointed parts constitutes the entire Pareto set. Okay, let's try one constraint problem. I'm trying to look for one here, should be, yeah, BNH is one where the constraint starts from number of objective plus 1. So until number of objective you have objectives, and then after that they are constraints. So they all have to be less than equal to 0, and we also again normalize, you see, So this is one we can try OSY. So let's try maybe 13 and 15. We are going to try, these are small size problems. Let's see, we have to go to NSGA2 and first 13 and we run. This is 2 variables, so it's fast. It's a mystery. These ones I don't have to combine all the codes, but the other one it was asking to put the code. I don't know why. Plots will come up. Yeah. So actually here there are 2 parts. I don't know whether you can see. One that goes this way and another one goes this way. There is a little kink here for this problem, and both of them are on the constraint boundaries. There are 2 constraints boundaries on that. Now let's do the 15. Okay. Yeah, I think this will be the last one I will show. Yeah, this one almost like a straight line. It curves a bit on both ends. Okay, so it's non-linear, but this one is more or less. I think this part from here to there is straight line, and then another feature comes up here and here. This is called SRN problem. So there are some of these are test problems, well tested in the literature, and we put it here as default for you to see. But if you have to use this to solve your problem, you can just put it like that.